All right. So our group was focused on extreme learning, a challenge to develop and apply novel math to capture, characterize, and predict extreme events in a warming world. And the extreme learning here has sort of two meanings. One is to learn about extreme events, but also this is going to require extreme advances in mathematics and in machine learning and other fields. And this is the team that worked on this. I want to thank them for their contributions. So the motivation here is that, as we've seen even in the past year, climate extremes are having devastating societal impact. We've seen extreme heat waves, uh, heavy precipitation and flooding in places around the world, droughts, storms, wildfires, and then compound events, for example, where we have uh, hurricanes happening with heavy rainfall or wildfires followed by devastating flooding. And as we know, the long-term prediction of extreme events is impossible with today's technology. Short-term is merely hard. And of course, by definition, if it's an extreme event, so the data is sparse. And with a changing climate background, the extremes are even harder to access. So even modest changes in the temperature can cause large changes in frequency and severity. And these may be concentrated regionally, even down to the city scale. So on top of that, tipping points may introduce qualitative changes in the climate background. So how can we understand future extremes without knowing their background? So that's one challenge that we have to contend with. So what machine learning and math research is needed? So we definitely need new machine learning techniques, novel loss functions. We need to understand their mathematical properties and robust algorithms to carry out training. We need to focus on scientific machine learning. So by that, I mean merging physics-based models with machine learning. We want to obey the laws of physics while focusing on the precursors and process chains leading to extreme events. We'll need new statistical methods for focusing on non-stationary and spatially distributed extremes. And then as we're doing this, it's going to require improvements in our existing physical models, the mathematics of them, as well as the computational techniques behind them, because often today's numerical methods can't really deal with extreme events within the models that they're trying to solve. We're also going to need new insights in characterizing and propagating uncertainty in all the relevant variables. So additional requirements are determining the data sources and the needs for future data collection. We're not going to be able to do this without experimental campaigns to go along with it. We also need to assess the quality of data. Not all data has the same level of accuracy. So we're going to need to convene stakeholder meetings, including infrastructure planners and operators, to identify the initial types of extremes for our focus and prioritize diverse stakeholder representation to maximize the value of research in improving equitable outcomes. This will lead to a lot of workforce development. It will require people that are well-versed not only in mathematics, but in the various domain sciences, in computational science, data science, et cetera. And hopefully we can form these interdisciplinary teams that will then broaden the diversity of the workforce. It will require huge computing, data storage, and networking requirements. As I mentioned, experiments, and there's a lot of interdisciplinary connections outside of mathematics to economists, environmental scientists, et cetera. We also need to create infrastructure and policies for verification, validation, and assurance. We want to make sure that these models are accurate and can be validated on prior events. So this current state of the art is there are some institutes. There's a NSF Institute on Weather, Climate, and Oceanography at the University of Oklahoma. There are other efforts going on in this space, so we certainly don't want to reproduce what's going on, but we want to extend and contribute to these efforts. Because assumptions that limit us, and I'm sorry I skipped over this, but are stable climate, the fact that most assumptions are Gaussian, And the machine learning methods that we have now are typically based on these Gaussian distributions and not the tails. So we have models of the future, but they're not based on very accurate data. They have imperfect and few data points. They use coarse grids, and we often have to make assumptions about the future that are just based on what we know about the past. And as I've mentioned some of the limitations with physics-based models that we currently have, but beyond the numerics and other issues, there's uncertainties in parameters, how things are parameterized, especially at the subgrid scale, multiple scaling issues, both in space and time, and then stale algorithms. So the grand challenges here are to assess the frequency and magnitude of local extremes within a globally changing world. So we need to anticipate future conditions that can incorporate global trends, tipping points, catastrophic events, create scenarios for probability distributions of extremes that incorporate unprecedented spatial and temporal resolution with better physical understanding, improve decision-making by accurate prioritization, advance scientific knowledge, and increase climate change resilience. So these are all the areas within these big areas that we hope to address. And then there are many stakeholders involved. So other government agencies, certainly NOAA, DHS, FEMA, public, private, commercial, and then hopefully get down to the local community scale.